Hello and welcome. In this video, we are going to talk about transfer learning. In a real-world deep learning project, instead of training and tuning models from scratch, we should always try to find existing deep neural networks which already have a good performance on similar tasks. We can adjust this existing model to our use case by reusing most of its architectures and parameters. This is the idea of transfer learning. Make an analogy. Transfer learning in machine learning is like grafting in agriculture. A small part is cut from the original plant and joined to a new plant, allowing the new plant to reuse the original plant's roots and continue growing. There are two major benefits of transfer learning. First, we can reuse already learned features of existing models. Transfer learning allows us to speed up training. Second, the pre-trained models already learned general patterns of the dataset. We can achieve good results even with a small dataset. So, consider transfer learning when you don't have lots of training data, or it is very expensive to produce them. After we have a brief overview of transfer learning, let's take one more step further and understand how to build it. First, find a similar model. Imagine we did the research and found out there is already an existing deep neural network for task A. Here is a simplified graph as an example. Second, reuse part of the lower layers. Lower layers of A are useful because they are learning the basic features, and it can be shared across similar tasks. For image models, lower layers often learn basic patterns like edges, shapes, etc. Third, replace some higher layers and the output layer. For various tasks, the output features may be different. We should replace the output layer to match our task output. How many higher layers we should replace really depends on the similarity of tasks. For very similar tasks, try to keep all hidden layers and only replace the output layer. The greater the difference between the tasks, the more hidden layers need to be replaced. You got the point. Fourth, training the model. After we decide the number of layers that need to be reused and replaced the output layer, we can start training this transferred model and adapt it to our specific task. First, we should freeze all the reused layers. After we freeze those layers, the training process won't change or update parameters for those layers. Only newly added top layers are trained. After a few epochs, we can unfreeze the entire model and fine-tune all layers together. In some cases, we should use a smaller learning rate to avoid changing too much the original fine-tuned model. Now, we have understood the general procedures to train a transfer learning model. Let's move to the practical example. We will use the Fashion MNIST dataset to demonstrate how transfer learning works. Our task is to classify t-shirts and pullovers from the fashion dataset. Two models A and B perform the same task. Model A will be trained from the ground up, and Model B will be transfer learning model. Their output layer should only contain one neuron for binary classification. We will compare the performance of them at the end. Training the ground-up model is easy. Simply filter out two kinds of images from the dataset and train the model. In order to train the transfer learning model, the base model or the pre-trained model is needed. Again, in a real-world project, this pre-trained model already exists and handles the similar task. we build the base model here for demonstration purpose. Let's call the base model B-base. B-base is a fully trained model that classifies the other 8 kinds of images. It has 8 neurons in the output layer. After we train the base model, we will build a transfer learning model on top of B-base. Let's move to the code. In order to train A, B, and B-base, we need to properly separate required subsets of data. The split dataset function helps us achieve this. For model A and B, we need to filter out records that labels t-shirt and pullover. Make sure to change the Y or label into 0 and 1. For model B-base, we need to filter out the records with labels excluding t-shirt and pullovers. Then, change the Y or label to 0 to 7. As a result, the first part variables contain 8 images. We will use them to train, test, and evaluate model B-base. And the second part variables contain 2 images. We will use them to train, test, and evaluate model A and B. Let's train model A first. We are using sequential models and feeding the dataset. After 20 epochs, the ground build model A performs 95% accuracy on testing data. Now, we build model B-base. It is a base model. B-base is trained on 8 different images. After 20 epochs, we build the base model. Now, we have our base model ready. Let's construct the transfer learning model B. First, we need to clone all the hidden layers architecture of model B-base, except the final output layer. Then, we add the final output layer with a single neuron. Because we only need our model to predict 0 or 1. Then, make sure to lock all the hidden layers' weights by setting the trainable parameter to false. We train our model for 4 epochs to only train the last layer parameter. Then, set all layers trainable as true and train 16 epochs to fine-tune all the weights. As for the final evaluation results from the test set, the transfer learning model gives us 96 accuracy, which improves 1% compared to the model A 95%. Cool, we see some improvements on transfer learning. In reality, transfer learning doesn't work well for small dense neural networks. It works better for deep convolutional neural networks. This is the end of this video. I hope you have better understanding of transfer learning. If you have any questions or want to share how transfer learning improves your project, please leave in the comments below. Please consider like and subscribe, and I will see you in the next video.